For example, if we would define us set D, for example, give me the D, the big D, the long dong. Good morning, fellow mathematicians, welcome back to another video. This right here is going to be the start of my series on my bachelor's paper, link in the description if you want to take a look at it. And today I would just like to do a little chill excursion into the world of set theory, basic set theory and operations on sets. We are going to dive right in. I'm going to break this up into many little snippets so that you can just rewatch every part of the video. And if you understand everything I've said today, then you're well suited for watching the rest of the series, because to be honest, my bachelor's thesis isn't really hard to understand. It's pretty basic, to be honest. So let's start off by the definition of a set, what that exactly is. Well, a set is nothing but a collection of different elements. For example, the set being your family is nothing but your dog and your mother, for example. I really don't care how your family is constructed. There's also something called a family of sets, but I'm not going to go into detail about that. So what could other possible sets be? For example, let's use A, being one set, as being nothing but 2 and 2 and 3. And here's a little restriction. We want to set for something called a set. Well, we want those elements right here to be distinct. That's something really important. Meaning, if you have a duplicate of an element in here, just get rid of one of those. So that means 2 and 2 and 3 is nothing but 2 and 3. So getting rid of all duplicates in this case, except for one. And I'm going to write my curly brackets like this. In normal case you would write them like those, but they are fucking annoying to draw. That's why I'm drawing them like those little snacks, Schlangen right here. Okay, what else could a set be, for example? Let's say we have another set B being nothing but 2 and 4. And those are going to be our example sets today. Another set, for example, being the empty set. The identity, the set theoretical identity element. It's a really important concept. It's called the empty set because there are no elements in the set right here. I'm going to talk about this set in a minute a bit more, just a little bit. And sets could look really quite different. For example, you could have a mapping inside, for example, the set of all mappings. Or for example, we could have the integers being nothing but -1, -2, 0, 1, 2, blah, blah, blah. So many, infinitely many elements. But we can also say, well, we can construct set as being just n, element of natural numbers, or -n, where -n is nothing but, well, the solution to n plus -n being 0, for example, with n out of the natural numbers at that. So you can construct, for example, the integers like this. This construction comes with many problems. When going into abstract algebra, it's just a little example right here. And now we are going to talk about operations on sets. So what could we do with those sets? For example, we could say that some element is indeed element of a set. How would you denote something like this? Well, for example, if we take a look at A, 3 is element of A, being denoted by this right here. You see? 3 element with this weirdly drawn epsilon A, whatever, \in A right here. We are going to write it like this. If you want to say 2 is element of B, just write it like this, for example, with a 2 and a B, and that's also element of our A. And also we can say that 2 sets are equal, for example. When are 2 sets equal? Well, if they have the same elements. For example, A and B are not equal, and you know the equal sign, so A is not equal to B in this case. But if our B would be 2 and 3, for example, well, then they are indeed equal. Okay, and if you want to say that something is not element of A, for example, element of some set, for example, the number 5, then you are just going to make a little line through the in sign right there. Okay, now I would like to talk about, well, Venn diagrams. They are just a nice little visual representation of sets. And we are going to denote Venn diagrams like this, for example. This first circle is our A, and this one right here is our B. And there are certain things that we can do on sets. For example, we can take the union of two sets. The union of A and B being denoted like this right here. That's easy to remember because it just looks like a U. And what is the union? Well, we just take the elements of A and the elements of B and put them into a set altogether. And if you take a look at the Venn diagram, what would this new set look like, being represented by those two circles? Well, it's just this whole thing right here by our definition. So the union of A and B is nothing but, well, 2 and 3 and 4, because our elements are distinct, and if we take the 2 into account 2 times, then we are just going to get rid of one of those. How could we rewrite this in a more general way? So if we have a set X in union with a set Y, well, this is nothing but some element X in here, a collection of elements. Well, and how could we write that? Well, we want X to be element of X in this case, let's put it like this, or we want our X to be element of Y. So this is just a definition. And you might notice something. This union right here is the set theoretical equivalent to our OR right here. There's also a set theoretical equivalent to our AND operator, you could say. I was talking about integers before, and I said they can be constructed like, well, we have this n, element of natural numbers right here, or we can have this negative n under the condition that n plus negative n is equal to 0, where n is element of natural numbers. But with this right here, with this new union stuff we have just derived, we can rewrite this like a little bit different. So we could say those are just the natural numbers with 0 in union with all the negative n's, where n is element of the natural numbers, and it's the solution to this thing right here, n plus negative n being equal to 0, just as a little matter of fact, so that you can see where stuff like this comes into play. And now we are going to talk about the intersection. Okay, so I've drawn a Venn diagram once again, where this right here is nothing but A and this right here is nothing but B. And I hope you can understand everything up until this point. Hard theory videos, you could say, really dry theory videos like those are quite hard to make for me, because most of the time I'm just jumping around and being happy and happy-go-lucky, but this time I want to make it a bit more serious. For my boys and my girls. Okay, now we would like to talk about the intersection of sets. Being denoted by, well, nearly the same as before. The intersection is being denoted by this little head right here. This little... I have to censor this. So the intersection of A and B. Well, what is that? Just imagine we are going to compare A and B, and we are just going to take the set, the elements they have in common right here into this new set. So the intersection of A and B, in this case, well, 2 and 2 they have in common, 3 and 4 are not the same element, so the intersection is just 2. How would you denote this in a Venn diagram? Well, it's just this little bit in between right here. And we can generalize this a bit more as just being, well, we have some, let's make 2 new sets, X and Y, the intersection of those, just like before, and well, we have a collection of some x's right here, under the condition that, well, x is element of x, and, in this case it's an and. No, it's drawn like this, I'm terribly sorry. So that's right here is the set theoretical equivalent to our intersection, and it's element of our y. So this is just, yeah, what we have. And now we are going to talk about something called the difference of sets. This is sometimes quite important if you want to take, for example, the natural numbers, which include 0, but you don't want to have the 0 into there. So you just say, we are going to take the natural numbers, but without the 0, so the difference of those two sets, you could say. Okay, how would you denote this difference of sets in a Venn diagram? Well, we have this A and this B, and the difference is nothing but, well, we take this A right here, and we are just going to remove the intersection, you could say, this part right here, and also the whole set B. So we are going to take A, but without all the elements of B. So that means the difference of A and B is nothing but this part right here. Sometimes it's denoted like this right here, but I prefer this way to write it, A and then backslash B right here. And you see in this case, we are going to take our A, and now we are going to take those elements, or just this intersection right here of those, and remove this intersection from A right here. Well, getting rid of the 2 leaves us with a 3 right here. And we can also generalize this. Let me think for a second. So if we have x without a y, well, what is that? That's just a collection of all the x's, where x is element of x, and where our x is not element of our y. That should do the trick. I hope I did this correctly. And now for one thing I don't want to forget. The difference of A and B is not the same as the difference of B and A, because if we take a look at the difference of B and A, well, what is that? This is the set where, well, we are removing all the elements which A has from B, so that means getting rid of the 2. So the difference of B and A is nothing but 4. So this operation doesn't commute. And now for the next one. Next I would like to talk about the term subset and superset a little bit. So what exactly is a subset? Well, let's say we also have the set C being equal to 2, for example. Well, then C is exactly a subset of A, because, well, all our elements of C are indeed contained in A right here. And we are going to denote this subset like this right here. This little, well, union turned to the side a little bit, and with this little line down here. So you could interpret this as the set theoretical equivalent to saying something is less or equal, you could say. And that's also something called a superset. So right here C is the subset of A, but that's equivalent to saying that A is the superset of C, or the mother set, or universal set, whatever. And if you take a look at this in a Venn diagram, well, we have our big set, our universal set A right here, and inside we have our little C right here. Here, that's how you denote it. And you can observe something. Well, you see, A is exactly a subset of A. But why exactly? Well, if we take A as a subset of A, that means all the elements of A are indeed contained in our universal set A right here. So that means that every set is the subset of itself. But here's something to take into account. There's also something called a proper subset. And something is called a proper subset if it's indeed a subset of some set, but not equal to the set itself. So this thing right here wouldn't be a proper subset because, well, A is indeed equal to A by the definition of equal sets. But C is indeed a proper subset, being denoted by just this right here without this little equal sign. And same thing here, A is a proper superset of C, if you say something like this. I don't know, I've never used this term proper superset before. But yeah, that's basically it. So that's just what a subset is. And also you can observe that the empty set is indeed a subset of every set. You can do this by a little proof by contradiction, yeah. Next, I would like to talk about something that's called the power set and also the Cartesian product. Let's start off with the power set, where the power set is just a set of all subsets of a set. So let's say we have the set A right here. Well, we're going to denote the power set by some kind of P. Write it however you want. And it's P of A, you could say. And like I said, it's the set of all subsets. By definition, every set itself is the subset of itself, and also the empty set is the subset of every set. So the empty set is indeed in here. Well, what else is a subset? 2 is a subset, so C in this case. But also 3 is a proper subset. And also our set itself, or you can just write A. That was a fucking ugly looking 3. Yeah, well, you see, we have 4 elements in here. If we take the power set of C, for example, it would just be a 2 and the empty set. If we take the power set of the empty set, it's just the empty set in this case, so there are no other subsets. Yeah, you can play around with this idea, and this thing right here grows arbitrarily large when you have a larger set, really large. I'm going to talk about this in a second. Now for the Cartesian product. Well, the Cartesian product is being denoted by this x right here, this cross product. You could say, no, it's not a cross product. It's defined differently, the cross product. Well, A and B, the Cartesian product of those is just a set of all pairs A and B, where our A is element of A and our B is element of B. Okay, how could you imagine that? Well, let's just take those as a little example right here. So we have this A and B right here, and we take the Cartesian product. Well, now let's just look for all the pairs. So we have 2 and 2 as a little pair. What else do we have? We have 2 and 4. And so on. So we have 3 and 2, and we have 3 and 4. Yeah, that's basically it. This is the Cartesian product. And this thing is quite useful because, for example, if we take the addition on the natural numbers, we are going to define this as n in Cartesian product with the natural numbers n being mapped to the natural numbers. So this Cartesian product right here is a nice way to do operations on sets, for example. Combine two elements into a pair and map them to a pair once again, or I don't know, to a single element right here. That's something you do in normal case. So if you just take the operation plus, for example, of the Cartesian product, for example, two elements, 2 and 3, they are going to be mapped to 2 plus 3 being equal to 5. So a pair being mapped to a single element. That's all that's really behind this. Next, I would like to talk about the cardinality of a set. What is that exactly? Well, it's just the number of elements in a set, so it's really easy to remember. And we can write the cardinality of a set like this, card of A, for example, or just with this little hashtag of A. Well, the cardinality of A is just 2. It has 2 elements in here. What's the cardinality of C? Well, 1. What's the cardinality of the empty set? 0. That's indeed the only set with a cardinality of 0. What's the cardinality of the power set of some random set? Where you can do the combinatorics on this one. So if you take the cardinality of some random power set P of X, you are just going to end up, well, with 2 to the nth power, and you can prove this by using mathematical induction. What's the cardinality of this right here, the Cartesian product? Well, this is nothing but the cardinality of the first set times the cardinality of the second set. So this is just simple combinatorics once again. So the cardinality of, I don't know, X in cross product with Y is nothing but the cardinality of X times the cardinality of Y. Yeah, that's all for the cardinality, and now for the last part, which was quite important in my paper. Next, I would like to talk about the term disjoint sets. And it's not hard to remember. 2 sets are exactly disjoint if they don't share any elements, if they don't have elements in common. For example, if we would define us set D, for example, give me the D, the big D, the long dong, as being 5. Well, those 2 sets are disjoint. 2 and 5 are not the same elements. Those 2 sets are disjoint. Those 2 sets are disjoint, but not those 2 and not those 2, because 2 and 2 is everywhere. So those are not pairwise disjoint. We can rewrite this ability to being disjoint in a little bit different way, or we can take a look at the Venn diagram. Well, if 2 sets are disjoint, that means they just look like this right here, A and B, for example. Well, but this also tells us something about their intersection. Namely, if we take A with the intersection B, then, well, that's just an empty set. That's what it means for 2 sets to be disjoint. And this right here is quite important in probability theory and stuff like this. It gives you a lot of information about the sets. Okay, and there's also something called a partition of a set. Well, how can you imagine a partition where you have a universal set, you could say, and then we are going to break this up into many subsets, all those subsets being disjoint pairwise. Okay, but if we take the union of all those subsets, we are going to end up with the original set itself. Let's just play this through with, for example, the set A once again, our little example set right here. So we want to use A, 2 and 3, and break this up into a partition. Well, one possible partition would be the set including the 2. and the set including the 3. That's once again an ugly looking 3. I'm terribly sorry, it looks like a snack. And you see, if we take the intersection of 2 and 3, well, the set including 2 and 3, that's just the empty set because they don't have any elements in common. That means they are indeed disjoint. And if we take the union of those, well, we just get our A once again. So can we even do this in the Venn diagram? I think so. Let's say this one right here is our original set A. And what we do, we break this up into, this set with 2 and this set with 3 right here. And if we take the union, we are getting A back once again. But if we just take the intersection, well, it's divided by a little line. Yeah, and this comes in quite handy in a lot of proofs. For example, since this right here is the set theoretical equivalent to saying something is and is, we can also say that, for example, if we take the partition of the natural numbers into odd and even natural numbers, we can say that no natural number is odd and even at the same time. I'm going to provide you with a little proof later. And that's basically it. Is there anything I've forgotten? One little notation-wise thing. Let's say we have a lot of subsets, some AIs being subset of some bigger set S. And we take the big intersection of those, I element of some interval, I don't know, of those AIs. This means nothing but taking A1, intersected with A2, intersected with blah blah blah, intersected with AN, for example. That's all it really says. You can do the same spiel with the union, a big union of a lot of subsets, and so on. I hope you did enjoy this little video. If you did, please like and subscribe and recommend the channel if you like. Support channel by buying those t-shirts I created, or I don't know, support me on Patreon. And up until the next video, have a flammable day this time. See ya!
Wie viel soll der denn kosten? 34 €.